A virus has a single mechanical objective: hijack a living cell and force it to build replication factories. Because viruses lack their own reproductive machinery, a cellular breach is an immediate matter of life and death for the host. Once inside, the virus unpacks. It drops its payload of foreign viral RNA or DNA directly into the interior of the host cell, expecting to seamlessly commandeer the local infrastructure. But the cell is not empty space. This diagram shows the intracellular alarm system. The structures labeled TLRs, or toll-like receptors, alongside RIG-I and MDA5, are specialized sensor proteins that patrol the cell's interior. These sensors act as a biological tripwire, specifically evolved to detect the molecular signature of foreign nucleic acid. The moment these sensors bind to the viral RNA, the cell recognizes it is compromised. Knowing it will soon be consumed by the virus, the infected cell initiates its final act. It fires off a massive volley of chemical messenger proteins called interferons. Here is the core mechanical truth of immunology. Interferons do not actually kill the virus. Instead, they operate as a highly toxic chemical flare. They flood the local area, forcing the environment to become completely unlivable for the invading pathogen. That first chemical flare is composed of type 1 interferons, specifically interferon alpha and interferon beta. This is the warn the neighbors signal, broadcast outward from the dying cell to every healthy cell in the immediate vicinity. Look at this sequence outlining the type 1 effects. When adjacent healthy cells receive the alpha and beta signals, they immediately trigger an antiviral state. Step 1 involves activating enzymes that begin destroying any incoming viral RNA, essentially killing the virus's blueprint. Step 2 forces the cell to shut down its own ribosomes. Ribosomes are the microscopic cellular machines responsible for building proteins, so turning them off completely closes down the manufacturing factory. In step 3, the neighboring cells upregulate their MHC class I expression. MHC class I is a surface molecule that displays fragments of internal proteins to the outside world. By pushing more of these to the surface, the cell effectively pins a wanted poster to its own membrane, making itself highly visible to passing immune patrols. Finally, the local lockdown summons natural killer, or NK cells. These act as early response assassins, scanning those MHC class I posters and immediately executing any local cell that shows the slightest sign of viral infection. By destroying blueprints, halting protein synthesis, and executing compromised neighbors, this local lockdown starves the virus of the exact biological machinery it requires to replicate. The infection is trapped at ground zero. It is easy to confuse this specific antiviral alarm with the general swelling or redness of a standard inflammatory or allergic reaction, but mechanically they are entirely different protocols. This matrix maps out various cytokines, which are the small proteins the body uses for cell-to-cell communication. As the chart shows, general immune responses have specific targets. Prostaglandins target local blood vessels and nerves to create localized inflammation. Meanwhile, cytokines like IL-1 and TNF drive system-wide blood vessel inflammation, which generates fevers. IL-8 recruits neutrophils, the white blood cells that act as first responders to bacterial infections, straight to the injury site. IL-4, 5, and 13 trigger the airway spasms and mucus of an allergic reaction. But notice the final row. Interferons do not target blood flow or airways. They uniquely and exclusively target the cells themselves. While other cytokines manipulate fluids, pressure, or trigger allergies, interferons are the only chemical signal dedicated to enforcing a total biological lockdown of the host's cellular architecture. If the local containment fails, the immune system escalates. It deploys type 2 interferon, known as interferon gamma. Released by natural killer cells and CD8 plus T cells, which are specialized white blood cells that hunt infected targets, interferon gamma acts as the ultimate systemic power booster. The top of this diagram illustrates the first effect of interferon gamma. It binds to macrophages and radically upgrades their phagocytosis capabilities. Phagocytosis is the process where a cell physically engulfs and digests large pathogens. By maximizing this ability, interferon virally turns standard macrophages into biological tanks. Next, it provides an intelligence upgrade.
Interferon gamma drastically increases antigen presentation by upregulating both MHC class I and MHC class II molecules. MHC class II molecules are found on professional immune cells and display swallowed foreign debris. This surge in surface displays allows the immune system to recognize exact viral targets with perfect clarity. Finally, the heavy infantry arrives. Interferon gamma boosts the lethal capacity of CD8+ cytotoxic T cells for targeted execution. Simultaneously, it forces the entire body into a Th1 response, a specific immune pathway designed strictly to fight intracellular pathogens, intentionally shutting down any competing allergy responses. The introduction of interferon gamma marks the precise moment a quiet, localized cellular lockdown is forcibly escalated into a weaponized whole-body war. Zooming out from the microscopic battlefield to the human patient reveals a harsh biological reality. The successful containment of a rapidly multiplying virus requires a massive toll on the host's own tissue. When a patient experiences worsening viral symptoms, deep muscle aches, severe fatigue, and inflamed tissue, they are feeling combo damage. The virus causes some destruction, but the majority of the collateral damage comes from the interferon response shutting down cellular functions, and CD8+ cells systematically executing the host's own infected tissue. Look at this clinical integration of viral pneumonia. The lungs are delicate. When the master interferon flow triggers an aggressive immune assault in the lungs, it severely damages the alveoli, the tiny air sacs where oxygen and carbon dioxide are exchanged. This widespread cellular death physically blocks gas exchange, leading to hypoxia, a dangerous drop in the oxygen levels reaching the rest of the body. If the battle drags on too long without a clear victory, the system enters an extreme failure state known as late-phase sepsis. Sepsis is a life-threatening condition where the body's overactive immune response eventually causes widespread organ damage and ultimately complete immune exhaustion. During this exhaustion phase, interferon signaling violently drops off. The CD8 cells suffer severe dysfunction and stop hunting. Because the heavy infantry has burned itself out, the patient is left in a state of intense immunosuppression, highly vulnerable to deadly, opportunistic secondary infections. In clinical virology, the severity of a patient's sickness is often a direct reflection of their own aggressive containment protocols, tearing up the local environment to deny the virus a foothold. But there is a final layer to this system. This extreme lockdown protocol maintains a constant background presence to facilitate cancer surveillance. Because tumor cells frequently contain mutated, abnormal DNA, they trigger similar intracellular alarms. Interferon gamma activates the same immune detection pathways, systematically destroying these rogue tumor cells before they have the chance to divide and form dangerous masses. From the instant foreign genetic material trips the intracellular alarm, to the localized shutdown of protein factories, all the way to the systemic deployment of heavy T-cell artillery, the defense relies entirely on this chemical chain reaction. The next time you experience the brutal aches and fever of a viral infection, you are feeling the master interferon flow at work, a successful conversion of your own cells into an unlivable fortress.